So my name's Mark, KA6WKE, and so for this month, now that we're all caught up, so for this month I wanted to cover the topic of radio frequency interference and what to do about it. We'll go over filtering, antennas, noise cancelers, using your built-in functionality of your radio to help with that. So what is RFI? Radio frequency interference is typically all man-made noises from electronic devices that broadcast. It's always pain in the rear to deal with. In some locations, it's so bad you can't even get on the air for any reason at all. You can't hear anything due to all this hash and other things that are going on around you. What we'll go over today is some of the techniques I've used at my station. I have developed over the years. So there isn't a single solution to the RFI problem. There are many steps involved in it, depending upon what the sources are. So for the vast majority of the sources we're going to talk about today, you have to deal with switch mode something, switch mode power supplies. We have variable speed motors in high efficiency appliances. Anytime you see the word high efficiency, think RFI. It's going to be there to some degree. So with that said, with that opening introduction, let's get going to where my station is. And this is what I started with. This is 40 meters on a typical evening. It's like this 24/7. Reception is almost impossible except for the strongest signals on the band. And when I first moved into this location 25 years ago, it wasn't that bad. But over the years, it got all kinds of worse. And I finally had to do something about it. 20 meters. 20 meters is exactly the same. A little less on the S meter, but you can see all these little striations going on. That's from a variable speed motor that's in my air conditioner. And we'll talk about how I resolved that at the source. First thing we need to do is to talk about what causes RFI. Now, this isn't going to be at the electrical engineering level. I don't think I could describe it well enough in those terms. But thinking about the amateur radio folks, the shortwave listeners, people that dabble with SDRs and things like this, I don't think they necessarily care about all the rigorous analysis of what causes RFI and how to measure it and all that stuff. They just want it gone. And that's what this session is about. But I still want to discuss how it's created, so you have an idea of why a variable speed motor is a problem, or a switch mode power supply is a problem. So what causes RFI? So the first thing is, you always hear there's two sides to every story, but there's four sides to every RFI story. And we'll discuss all of it because RFI needs to be tackled in several places. At the radio, and when possible at the source, if you have access to it. Typically, if you're going to be filtering at the source, that's usually something you own. I wouldn't go to my next door neighbor and say, hey, can I put all these chokes on your air conditioner because you're ruining my receiver. I don't think that would go very well. But we're going to talk about common mode RFI, and that's the type that gets coupled into cables that connect everything together, whether it's your air conditioner, cables to your computer, cables to your radios, anything along those lines that makes its way back to your radio. Then there's the type of RFI that's actually transmitted within the amateur radio bands or the frequencies that you're interested in listening to. There's only real two solutions to that. One is trying to filter at the source, if you can do that. And then the other thing is using a noise canceller. And we'll go over using a noise canceller later on in the session. It's also possible for your radio transmitter to be the source of RFI to other electronics in your home. I've read on the internet, I key up with 100 watts and my washing machine stops, or the dishwasher turns on and things like that. The techniques that I'm going to show you in this session on filtering at your radio also work on appliances or other things that are suffering RFI. It's the exact same technique, exact same types of filters that you'd use. So that's really all the bad news. There are many avenues of RFI in today's world, and it's only going to continue to get worse as time goes on, as we become more and more of an energy efficient nation environment. The good news is one or two techniques fixes all of it or can greatly reduce it. My goal here is to try and eliminate it if can be, or reduce it enough that you can get your enjoyment back. So let's talk about what causes RFI. The root cause of RFI is what's called pulse width modulation. Now, we're all familiar with different modulation techniques like AM or sideband or FM. It's similar to that, but what this involves, what pulse width modulation involves, is turning something on for a short period of time and then turning something off for a period of time. So what this does is it effectively chops up the power going to, we'll talk about like an electric motor, where the motor stays on for a short period of time, then stays off for a short period of time, then comes back on. And that's what creates the variable speed of an energy efficient motor. And the on time, the more on time you have, the faster the motor goes. So it's quite possible that if your energy efficient heater, say, is running full blast, that it's on all the time, that your RFI might go away. Okay, so that's one clue you can have. The other clue you can, other test you can run on your heater, air conditioner, whatever, is causing it to vary the speed. And if the noise pitch changes, or as you can see in my waterfall, if the striations get further apart or closer together, you've found. But the problem is, it's this abrupt shutting off and turning on that causes the problem. Now, switch mode power supplies work in the same fashion, and that's how they are so energy efficient compared to a linear power supply, like the old Astron 20 amperes and things. And then they also, Astron also creates a switch mode power supply that's, a third the size and, 10% of the weight of a linear supply. And that's how they make things so efficient. So anytime you see the words energy efficient, immediately think RFI. What I didn't do with my own air conditioner was ask the heating and AC and heating company to take me to a place that already had this unit installed with a portable radio and check it out. I would highly recommend you doing that before purchasing a unit. It's much easier to nip it in the bud in the beginning than it is to have it installed, find out 6 months later you got a problem. Now, I worked with my AC company. They were fantastic. They actually I have a big Lennox unit, and they contacted Lennox, described the problem to them. They brought out one of their engineers to look at my situation with my station and what's happening with the unit. And they put together a filtering kit for it. And although it improved things, it didn't really take it away. So we'll talk more on solving at the source later on in the session. So here we are creating all these square waves or pulse width modulation technique going on to keep energy efficient. But what happens is, what creates these square waves is actually an infinite amount of odd harmonics. They all get added together and eventually they become a square wave. So say, for example, your variable speed motor is pulsed at 1 kilohertz. If there isn't any filtering on the wires connecting to the motor or the controller or anything like that, it'll produce RFI starting at 1 kilohertz, then 3 kilohertz, then 5 kilohertz, and it just keeps going. From my experience, once you get past about 17 megahertz in HF, that it drops off enough that it doesn't really become so much of an impact. But it's definitely an impact on the low bands from 160 meters. Yes, I would say even AM in some cases, the AM broadcast band up through about 17 megahertz. It can still be a problem. But I've heard from other hams where it was all the way up to 50 megahertz that they were having issues. As it goes higher in frequency, its intensity starts to drop, but it doesn't drop by a lot. Spectrum analyzer display, it just keeps going off to the right here, and it's going to take a long time to get a minus 100 dB compared to this main spike here. Most modern receivers can go as low as almost minus 140 dB. So we still have a lot noise that can be transmitted before our receivers receive it. So that's going to go on for a while. So that's the main cause right there. And digging into the electrical engineering side of things, I just don't think is that important. What we want to talk about is how do we get rid of this stuff so I can enjoy amateur radio or shortwave listening, or what have you. So let's get started on this. The first thing is you're grounded. You have to have a decent station ground, and we'll talk about how I built mine. Now, what I mean by decent is the best you can do. So for my location, I only have enough room to install a second 8-foot ground rod dedicated to my station that's connected back to the house ground near the power panel where all my the breakers are. I can't add any more ground rods around my property or any place like that. So the first thing to do is to make sure your own home is clean. And you do that by shutting off all the breakers in your box except for the main house breaker. So I have a 200 amp service, a 200 amp breaker at the top of the box. You leave that on. You shut off all the other breakers going to the different circuits in your house. You put your radio on a battery, and then you turn on a circuit, check your radio to see if there's noise. And you just keep doing this until you find a circuit where all of a sudden you've got RFI. So somewhere on that circuit, you've got more than likely a switch mode power supply. For myself, when my kids were getting their first jobs in that, they would buy a new monitor or something for their computer, and I would go and ask them, okay, what did you buy lately? And put ferrite on those power supplies. Make sure your own home is clean first. The second step is building your ground. And I've tried all different types of grounding styles. I've tried a star ground, where each component that needs to be grounded has their own ground connection back to the single ground rod. I've tried a bus style where you daisy chain, one ground lead from each component all the way to the ground rod. That didn't help. But this technique that I thought about helped greatly. So what I started with was a large sheet of copper. And I went down to my local metal supply store, and they have copper remnants around. I think I spent $20 for this sheet. It was 18 inches by 48 inches long. Width was perfect. 18 inches is fine. 48 inches was too long. I needed to trim it off, which you can cut with a pair of regular tin snips. I bent up one corner. The ground was going to be attached up in the upper left corner. From there, I prepared the panel. So I had one of these Harbor Freight punches, those $5 punches that seem to last forever. I bought a bunch of stainless steel screws, machine screws, nuts, and flat washers, and I punched holes every 3 inches along the back, all the way along the back, and then mounted the hardware as we can see right here. So each of my radio components, my rig, my antenna tuner, my noise canceller, my power supplies, They all get grounded to one of these lugs. And I did the whole length for future expansion. So you could do just what you need, but I can pretty much guarantee sometime in the future you're going to want another ground lug, and then you have to tear everything down and punch a hole and put the parts in it and all that. So just go ahead and do the whole thing and save yourself some time later on. So then it was doing a trial run on fitting my equipment. So I have an ICOM 7600 on the left. I have an LDG 1000 Pro 2 on the bottom, and on this here, this is the MFJ noise canceller. And as you can see, it created a very nice ground plane to put everything on. I thought instead of having a 1-inch braid connecting and going off to the ground rod, which is about 9 feet away, I thought this would create a much lower impedance at RF frequencies to have a nice big copper sheet under the equipment, providing a low impedance path to the outside world. Now, the next step is to connect to the ground. So I use 1-inch braid, and as you can see, keep them as short as possible. And each component connects to each lug. Off to the right, 35 amp power supply for the rig is attached here. There's another 20 amp supply that provides power to the accessories, and another radio that is attached here. So anything with a ground post gets attached to this copper sheet. Now the next step, once you have your ground all situated, you can test it. Plug it in and see what your noise levels are like. Maybe you'll notice a drop right away, and this is good. So you'll know you're on the right track. Even if you don't notice anything right away, you can't tell necessarily by hearing it or by looking at your waterfall display. Keep going. It gets better. Is your station anemic? And what I mean by that is, does it have enough iron? And that's where the different types of ferrite material that it's in different forms need to be applied to all the wires, and I mean all cables. Anything that connects to your radio needs filtering on it. This is not necessarily this is not a session on Palomar engineers or an advertisement for them, but I was at the Yuma Hamfest here in 2019, and Bob Brame, I think that's how you pronounce his last name, he's the owner of Palomar Engineers, did a very thorough presentation on RFI and RFI resolution. I knew I had a big problem with RFI, but honestly, I'd pretty much given up. I had my doubts that buying all these stuff and putting it on my rig and that it was going to make. Unfortunately, I did not find what I want at the Hamfest, at the swap meet at the Hamfest. So I still had some money laying around, and we know it's against the amateur radio creed that if you go to a Hamfest or a swap meet, yet you never return home with cash. So I decided I would just, what have I got to lose except getting rid of the noise? So I bought everything he recommended and then some. This here is a 1.8 megahertz to 30 megahertz line insulator that's used on my coax that comes into the shack. I have another one similar that only works from 3 megahertz to 30 megahertz that I use on the other antenna. That's not going to be part of this discussion, but it's very helpful to have one of these. So how do we get started? Well, we get started by taking all the wires, all the cables that connect to your radio, and we start winding wires through the different styles of ferrite. So this is what's called a toroid or a donut. Some people call it donuts. And this is the main power cable to the 7600. So I wrapped it through as many times as I could, leaving about a 6-inch pigtail to the connector to the radio. Okay, you don't want to get your ferrite too far away, because then this cable here, this part of the cable here, can actually become a short antenna and possibly pick a common mode RFI past your toroid. You don't want that to happen, but 6 inches seems to be fine. So there's different sizes. This is a 2.4 inch, a larger one, so I could get the connector through. Actually, I think I wired it through the other way, which had a smaller connector. This one here, this is a power supply connector. This is for the noise canceller. This is for the antenna tuner. This actually goes to the antenna tuner. Control cable and power. That comes from the rig. And this is the other end of the tuner control cable. So there are ferrites on each end. For all of your components, you have ferrite as close as possible to the connectors that connect to those devices. Now, I had another issue with RFI. I live less than a mile away from a 50 kW AM broadcast station on 760 kilohertz. It's so loud that I've actually measured the AC voltage on my 40-meter loop antenna that's up at 35 feet. And I measure 3 volts coming off that thing. There's a lot of additional broadcast RFI that I'm receiving that was causing the antenna tuner not to tune properly on the lower bands. Probably because it was using the 760 kilohertz or maybe its second harmonic. Yes, AM broadcast stations have harmonics. They're just very low, but since I'm so close to the transmitting towers, it was powerful enough that I believe it overloaded the sensing circuits, the SWR circuits inside the tuner, causing it to claim it had tuned to 1-to-1, but the SWR on the rig was 4-to-1 and 3-to-1. So there were some other things going on. I'll explain how I solved that later. As you can see, I use some wire ties to keep things neat, to tie things down. You can put multiple turns through a donut, and each turn is one pass through the hole, or in this case, one pass through. This is a clamp-on, because I couldn't cut the cable necessarily to put an inline filter. Clamp-ons are great for that, so I put as many turns as I could through the filter here, the clamp-on ferrite, and then I used a wire tie to hold it in place. Now, this is the secret to greatly increasing what's called the choking impedance. And simply put, that's the impedance to RFI for every time you go through. If you could do 2 turns, it makes the choking impedance 4 times higher. If you go 3 times, it makes it 8 times higher. 4 makes it 16, etc. The goal is you want to have a choking impedance that's 10 times greater than the characteristic impedance of the cables that you have. So for coax, that's 50 ohms. You want a minimum of 500 ohms. And in the data sheets tell you, one turn is equal to, say, 25 ohms impedance. Now you know how many turns you have to go through to get it to at least 500. Now, most of mine ended up being over 1,000. Which is, that's even better. That's free. Just as long as you have the cable length to do this, put as many turns as you can to get as much impedance as possible. So then I started fitting things on the back of the radio and taking a look, and here we go. We can see the filter going power supply to the back of the noise canceller into the antenna tuner with its 6 inches. Same with the tuner control going through here and the DC power going into the back. So we keep going. So I had more. I had to deal with the TR switching for the back of the noise canceller. These two go to my West Mountain radio. So you can see I have multiple cables, multiple connectors going to different pieces of equipment through a single clamp-on connector. And that's fine. You can do that. Save ferrite. You can fill it up. Just make sure you don't need a pair of pliers to squeeze it shut so you don't compress anything or possibly cut the insulation, because it is conductive in there inside the ferrite. Let's see. So this is the back accessory connectors to the 7600 that I use for frequency shift keying, TR switching, etc. And whatever else, is on the back of those connectors. So here, this one here is for CW. This plugs in the back of the rig blaster. So I've got, a toroid here wrapped with as many turns as I can and tied off with a wire tie on both ends. This end goes to the rig, this end goes to the rig blaster. So you want to have filtering you want to make sure you have filtering on both ends. Because if you have filtering on just one end, say just on the radio end, the component you're connecting to could still be overcome by RFI and, like my antenna tuner, just not function correctly. So you want to make sure you have filtering on both ends. Dealing with the AM broadcast station. My thoughts were, since that signal and its harmonics are so strong to me, since I'm so close to the transmit towers, I needed a different mix to try and filter that off the outside of the coax. That's where I believe a lot of the interference from the stations was coming from, was from the braid of the coax, or in my installation here, coupling through the ladder line, which then connects to one of those line insulators I showed earlier, into coax into the tuner. So my thoughts were, that's where I'm receiving the RFI from the broadcast station that's impacting how the tuner's functioning. Well, given the frequency of the broadcast station, you need to have a different mix. All ferrites are made from typically iron powder and some other things mixed into it, and they work best over a certain frequency range. So for HF, for high frequency, 1.8 megs to 30 megs plus or minus, mix 31 is the most commonly used, and that works the best. Mix 75 is for the lower frequencies, below 1.8 megahertz, and I don't remember the lowest possible limit for the mix 75s. So in order to block a much broader range of frequencies, I needed to have a stack of toroids of different mixes put together to broaden the filtering range, to broaden the ability to create a choking impedance. Okay, and then write on them what they are, because you won't remember 3 months later, what mix is this? You can't tell by looking at a toroid and tell you what mix it is. You will forget, so I just write on mix 31, 75. Okay, so now starting to work on the coax side of things. So this is how filtering as close as possible to the antenna tuner is put together. So these two connectors go to the back of the antenna tuner. There's two inputs on my antenna tuner, and there's two outputs going back to the radio. Here, I bought some RG400, 6 feet long, and wrapped through, I think, 7 times before using wire ties to tie them off and keep things neat. The thing to be careful with coax is you can't pull it snug tight like regular wire can. Remember the other toroids, I had it really tight around the donut. You can't do that with coax. You have to avoid what's called its minimum bending radius, because if you do, what'll happen over time, very slowly over time, the center conductor will start to migrate through the insulation and possibly touch the outer braid. So you don't want that to happen. On the data sheets for coax, they'll tell you. So I know for the 400s, it's about 3 inches, so I left it at 3 inches. I put both connectors through there. That's totally fine. And then just use a whole bunch of wire ties, to keep everything together. So on the back of the tuner, it looks like this. The antennas connect here. One antenna that I use for 160 and 80 meters, and the other antenna is 40 through 6 meters. I've also, up here at the top, I've also put a coax jumper that was 2 feet long and passed it many times through another toroid here that goes to the master antenna for the noise canceller. I didn't do one on this end. I did not put a toroid on this end because this is only about 8 inches or so long, so I didn't worry about that. So when it's all said and done, this is what the back of my station looks like. There's more ferrite, even on the USB connector. I bought a high quality USB connection back to the computer. There is many turns through a clamp-on ferrite here. And also at the computer end, at the USB. Sometimes you can buy USB cables that have the little bump in it that contain a filter. I don't know if they're good or not, so I went with what I knew that worked. Let's see, there's another broadband pre-built filter that comes out of the MFJ into the input of the rig as well. I didn't bother. Again, this is too short. This is only like a foot long, so I think it's too short. I didn't need to put more ferrite on this end. There's ferrite coming off this is for the noise antenna that's outside, and I'll discuss that later, a little later. I have a receive loop attached to the back fence of mine in the backyard, and this is the power injector, and it has ferrite. It's hard to tell, but it's right here for the power. There's also ferrite on this. I forgot the type of coax this is, to connect to a broadcast band filter here. So there's ferrite there. This is only about 8 inches long. And this little 75 ohm pigtail connects right here. That's for a receive-only antenna, and I'll be demonstrating that as well. So after all the filtering was done, this is what I have on 20 meters. This is 20 meters still. And the striations you're seeing here are from my air conditioner. This is very common pulse width modulation, energy efficient motors. Switch mode power supplies can look the same way. Maybe they're not as fat or whatever, but they sound the same and they kind of look the same in your waterfall. And they sound the same in the audio. So what did I have to do? This is where I had to go to the source and filter there. This is how I did it. I took the remaining clamp-on mix 31 toroids that I had left over from inside the house, inside the station, and I clamped them on all the wires. That led to the compressors here. It's also a variable speed compressor. This fan is variable speed, and I had to remove the grate and the fan. This thing is so large, I could actually kneel inside and attach all these clamps-ons. You can't really tell in the picture, but they also have wire ties on them to make sure they stay closed. But this is one of the situations where I could not put turns through the ferrite. I could only put one turn, one pass through the ferrite, and I needed a bunch more ferrites to get the choking impedance that I needed to help quiet things down. I don't know what these wires, exactly what each wire does. I don't know which one goes to the motor. I don't know which one is from the controller. And it really doesn't matter. What matters is trying to filter all these exposed wires, putting ferrites on them as much as possible. So what's the results now? Well, let's take a look. So this is 20 meters after filtering the AC unit. All right, so that's dealing with ferrites, where to place them, how to place them, why they work, and make sure that you just understand that you can only do so much at your rig inside your station, that you may have to go to the source and apply filters there. Okay, let's talk about some ratios here called signal to noise ratio, and how using a receive-only loop, your RF gain control, can help you in reducing the amount of noise that you have to listen to. So what is signal to noise ratio? Let's say that the last station that was talking, that was at the noise level, you could hear them, but you also heard the noise at roughly the same intensity. That's a low signal to noise ratio, okay? The other station that was talking, that it was very clear, his signal strength was much greater than the noise, that's high signal to noise ratio. That's what we're going for, okay? You want to amplify the signal that you're interested in, but not amplify the noise and make it worse. So one way to do this is with a receive-only loop, and this is mine. This is a W6 LVP receive-only loop on a rotator at the back of my house. This is where it's strapped to the fence. It's incredible. How this works is, compared to a regular full-size antenna, is that it works in the magnetic portion of the signal. And there are two components to your radio transmission, or a radio transmission. There's a voltage component, and then there's a magnetic component. RFI predominantly lives in the voltage component of the signal, and it's always vertically polarized. I've never been able to find out exactly why it's always vertically polarized, but it is. And that's what makes vertical antennas slightly noisier than a horizontal. The receive loop, on the other hand, works in the magnetic portion of that spectrum. As a transmission goes through space, free space, or to the receive antenna, it alternates back and forth between a voltage and a magnetic, and voltage and magnetic, and goes all the way through. You don't have to have both of those components in order to receive the signal and understand it. A receive loop, or also known as a magnetic loop, listens to the magnetic part, which is so much quieter. The other benefit is that they're highly directional. If you want to peak a signal with a loop, the maximum strength of the signal will be within the plane of the loop. Okay, so in this direction. Say, for example, I get RFI from my neighbor's house. I don't know what they have. It's intermittent. But what I can do is I can rotate it so the null, where the loop is deaf, it's very deep, and that's in this direction. I know this is going up and down, but think of it going from this house to my shed. It's going through the loop in this fashion. It's 90 degrees to the noise source. I can rotate this around. It's typically around 47 degrees for me. I can completely eliminate that noise source while still working, still receiving the signal. Now, I'm not going to have the same signal to noise ratio because the antenna may not be pointed directly at that signal source. It might be off to the side. But with the elimination of the noise, the signal to noise ratio increases. So there's two ways to improve that. One is to have a much stronger signal than the noise level, or one is to have a much lower level of noise to increase that signal to noise ratio. And that's what we're going after here. So here's an example of switching between a full-size antenna for 80 meters and the receive loop. A magnetic receive-only loop antenna and a full-size HF antenna. So what is signal to noise ratio? Right now, this is a good example of a high signal to noise ratio. The station's a lot stronger than the surrounding background noise that we're seeing. So he's clear. You can understand what he's doing, but you can also hear a lot of background noise. And we can't hear any of the other stations trying to check in. So magnetic loops work on the basis of the magnetic part of the radio frequency spectrum. So when you transmit your signal, it has two components, a voltage component and a magnetic component. RFI also has a voltage component, mostly a voltage component, and not so much a magnetic component. And no one seems to understand why, but it does. It's also always vertically polarized. So using a loop, a receive-only loop that only works on the magnetic portion of the spectrum,
You see the S meter drop to almost nothing.
helps reduce all kinds of noise. And we'll demonstrate this here right now.
Okay, Mike, I had the wrong receiver on. I got PQM in Glendale, Oregon, but I didn't get the prefix. One more time, please, Mike. Okay, got it. Thank you very much. I just filled it in. I'm listening several different ways. I'm listening on two SDRs. and on my regular radio here, and different people come in strong on different ones, and a lot
So
of
you
people
can
don't
hear
come in at all.
the
It is a
signal,
rough
the
night.
overall signal strength has kind
Late
of dropped in
monitoring
the
session
waterfall,
for the Western Public Service System. Looking for
which is
late
okay
calls,
because
missed
the
calls,
signal
or
to noise
visitors. Come
ratio
now.
actually improved. You can hear a lot less background noise. And there's a station near the noise.
Gary, there was somebody in there, but what did you say? I heard Sherman. I don't know if Dave got him, but I'll write him down on my late
Try
log
and
because I did hear him.
time
Over.
this here.
Gary. There may have been a station trying to check into the Western Public Service System. Come now.
Okay, I don't hear anybody.
K6 PQM, did you hear him? I'll try that again, Mike. Give it to me again and I'll write it down.
Yeah, we're just not able to hear the other station.
Got it.
So this is the concept of signal to noise ratio.
Can you confirm with him, please?
And having a receive-only loop antenna really combats local noise. And the other benefit is if you can put your receive-only loop on a rotator, you can rotate the loop around and actually null things out. Some of the
Mike, did he,
RFI I receive is from my neighbor's house. So I point it broadside to my parents' house. Let's see if we can null the station out.
Were those stations trying to check in? Come one more time.
Yeah, he might be very local to me, and I might not be able to.
Okay, there were two. I got Whiskey 7 Alpha Alpha Bravo. Is that a Roger? Okay, I think I have now Whiskey 7 Mike Alpha Bravo. Is that correct? Okay, it is a very rough call, but
Okay, so I was able to rotate the antenna around to weaken his signal. And a mag loop has the ability, or by its design, has very deep nulls in 90 degrees of the plane of the loop. And there you have it, signal to noise ratio and the benefits of having a receive-only loop to combat radio frequency interference and improve your listening pleasure. The other thing about signal to noise ratio is there's man-made noise and there's natural noise, natural static that's always present in high frequency bands. The mag loop, as you saw, can help reduce that greatly to make the signal to noise ratio better. Remember, it's about signal to noise ratio. So you want to have the strongest signal with the least amount of noise in the background. So let's first take the RF gain control and push it all the way counterclockwise to minimum. And then you turn your volume up to about 3/4 of the way to full volume. You don't want to be at full volume because a lot of the audio amplifiers inside HF radios have a high amount of distortion at full volume, something like 10%, which I think is pathetic. But you know, at the time, for a $2,500 rig, you'd think you'd get at least 1%. But anyways, I digress. What you do instead of this is you leave the volume where it is and you start increasing the RF gain until the signals become You might have to turn your volume up. So right about there, it's perfectly intelligible in my headphones. So this demonstration is how to use your noise canceller. It's a very effective device, provided you have an effective noise antenna. The little telescopic antenna that comes with some of these noise cancellers, I don't know why the manufacturers even include them. They don't work. Don't even bother with it or waste your time. You'll just get frustrated. Your noise antenna has to be able to capture the same noise as your main station antenna. And what the noise canceller does is, by adjusting the different gain, the noise antenna gain and the main antenna gain, so that the noise levels are at the same level, the phase is what takes the noise and flips it over, inverts it, and then mixes it back together. So when the signal leaves the antenna jack in the back into your receiver, the noise has been nullified or removed. So I've heard a lot on Facebook and other internet sources that people claim that a noise canceller can only cancel a single noise at a time, only one specific noise. So with this demonstration, I'll show you how I'm going to null out WWV on 10 megahertz. Now, right now, it's coming in very well. You can see it's like 20 over 9. And the noise antenna that I have is 65 feet of wire, helically wound on a 9-foot crappie fishing pole, carbon fishing pole. And that's strapped to the side of my fence between houses here, where I can get some RFI from my neighbor's home. So let's demonstrate how this can work. So the first thing you want to do is you want to set your gains to 0, and phase can be anywhere, that's fine. So we'll get started. You can still hear WWV in the background. It's very weak. Turn that volume up a little bit. Now we'll start using the noise canceller. So what I like to do is start with the noise antenna, and I want to bring the signal up so it's about an S3, give or take. Okay? Now go to your main antenna, the station antenna, and also give it to about a 3. Right about there should be so fine. Put the noise antenna back to where it was and start playing with the gain, with the phase. So I'll move it out there for a bit. Need to have some more gain here. Okay, so now we can see the phase has been added together to make the signal stronger. Now we'll just start moving the phase one way or the other till you notice a drop in the signal. And it's right about there. Now once you reach this stage, you just want to rock your gains back and forth until the signal starts to disappear, like that. Now we're still going to hear WWV in the background because this is coming from skywave. And what's happening is because of the ionosphere, the phase of the signal is arrived at my noise antenna and my main station antenna, which is a full-size 40-meter loop at 35 feet at different angles. So in order to fully reduce WWV to nothing, I have to keep with the phase control and possibly the antenna gain. So you can see phase changed and WWV came back. So this is with it off. That's the strength. We're looking over 9.
22 minutes. Coordinated universal time.
And this is with WWV nulled. Now, I've had good luck with local noise sources where the phase doesn't change. It's direct. It's direct to both antennas at roughly the same intensity, and it'll just completely null the noise out. But this is on a per band basis. If I go to 80 meters, for example, it will need to be retuned. Or another, maybe go to 75 meters. But what I found is once it's set, for the most part, it can cover the entire band. We can still see the phase changing a bit with WWV. So if we take it out of phase, we can get the signals to add. So there we go. Now we're making the two signals. The signals between the station antenna and the noise antenna are actually adding together to give us a strong signal. It's not as strong as going straight to the main antenna. Like this one is bypassing the noise canceller. But now here you can see that it's not bad. So now we push the phase angle back in and we go find the spot where it was. Okay, signal's coming up here, so that's probably what's happening. Yeah, I seem to have lost the spot here.
24 minutes. Coordinated universal time.
That's not bad. So here we are with it off. And here we are with it back on. So we successfully took a very complex signal that has a carrier, 2 sidebands, some audio frequencies in there, tones, well, there are also audio frequencies, and we're able to reduce to almost, still hear it in the background, still usable signal, but imagine having 40/9 noise or 25/9 noise from a sodium vapor. So the thing about the noise cancelers is they take practice. I've had the MFJ for probably 3 years now, and I've gotten really good at it. So because I've had a lot of opportunity to practice with it. And that's the best way to remove any type of electrical interference that's broadcast within amateur radio bands. You could null it out and get rid of it before it goes to your receiver. I did have to do a modification to it. I added a second relay in the back inside the MFJ because when I would go to transmit, the receive antenna was not grounded, and I ended up blowing out. There's a little light in there for protection. I ended up blowing that out. I ended up blowing out a couple of the J310 JFETs in there. So I pretty much had to rebuild it, put an extra relay in the back so when I transmit, it grounds the noise antenna as well. Okay, so that's the noise canceller. So what are the results? I showed you 20 meters after I got the AC done. This is 40 meters. Later in the evening, typically when it's noisier around my location. And this is taken during the North American QSO Party CW contest. So you can clearly see that all the RFI is gone. Lots of signals on the band. I'm using my RF gain control, background noise, the always present static minimized. You could hear the signal, the CW, nice and clear, and there's no striations, there's nothing. This is just about as good as I'm gonna get at my location. All right, and that's it. That's everything that I've done at my station to, in my case, I was able to eliminate all of my RFI problems. My neighbor's house is about maybe 20 feet away from my station antennas. You know, we live pretty close together here in Southern California. I hope you enjoyed this. We found it very informative. I'm hoping that I'll hear from you. You can find me on Twitter at KA6WKE. You can search me there. You can leave comments below the YouTube video when I post it. You can ask questions there. If you'd like to show this video, maybe during a club meeting, you feel free to do so. That I would like if you would put in the comments below what club, where it's located, and when you've shown it. I think that'd be pretty neat. Please subscribe to my channel. I'm working on getting to 100. If I get to 100 subscribers, I can get a custom URL to the live stream instead of the gobbledygook one that I have now. That would be greatly appreciated. And also click on the little bell to the right. So when I do have time and I just do a pop-up stream and going to do a repair or something, that you'll be notified that I'm live. So with that, I'm going to say 7-3. Go clean up your RFI. And please let me know the results. You can also, not just on Twitter, you can reach me at mark@ka6wke.net. Anyways, 7-3.